Good afternoon, folks, or good morning, or perhaps good evening from wherever you happen to be joining us. It's fantastic to have you here on today's webinar. As always, my name is Pete Dickinson. I'm the product manager here at Emesent for the Hovermap product. And today we're diving into a recap of the Hovermap solution and, of course, how that integrates and transitions over to Maptek. So it's fantastic to have our CEO and co-founder, Dr. Stefan Schraber, and Jordan Herman, who's technical specialist with Maptek, joining us along today. So quick housekeeping, just remember that everyone will be on mute, but please go ahead and use that question box. Love getting the questions. We'll hit on them as we go throughout the webinar. Always love to mix those in, keep the presenters on their toes, always fun for me. And if you also watch that Q&A box, you can also upvote those questions you would really like to get answered. So if we don't cover them as we go or throughout the presentations, we'll try and get to them at the end. And so we have, of course, Stefan and Jordan hanging around, but we also have Dr. Jeremy Safania, our technical evangelist, here to answer some of those fieldwork and best practices questions should they pop up. So feel free. We know we've got quite the crowd of people joining us today. Hello and welcome if you're joining us live, and of course, big hello if you're joining us from the recording. So this webinar will be recorded and it will be shared afterwards. So if there's anything interesting you want to revisit, you will get that chance. So yeah, of course, let's get underway. We've got a fantastic lineup of information for you today. Stefan, our founder and CEO, he's been around drones and autonomy for so long. They were gas powered when he got into it. He'll give us a great recap of what Hovermap does, our autonomy, our world-class point clouds, and what the reason many of you will have joined today, whether you're an engineer, a geologist, whatever role you might have, that transition of our point clouds, that rich, beautiful Hovermap data through to the Maptek solution in Point Studio, and have a look at some of those amazing features. We're going to get a live demo from Jordan, so say a little prayer to the demo gods that's going to all run smoothly and perfectly, as I know it will. But if, many of you may have already met Jordan if you're familiar with Maptek. He's been with Maptek since 2005, so everything from laser scanner hardware production and sales and customer support through to high-level implementations, working with a lot of customers. So I imagine many of you will have met Jordan. As you'll see when he does this demo, he knows point clouds and the Maptek software back to front. And so geologists, geotechs, engineers, surveyors, think up those really hard questions. Jordan is dying to get into those. And so without further ado, let's hand over to Stefan and get started today. Thanks, everyone.
Great, thanks, Pete. Hi, everybody. Great to be here today and really excited to be a part of this webinar. I mean, obviously, we've been focusing on automating the collection of data in challenging underground environments through Hovermap, and that's part of the picture. And then obviously, partnering with the likes of Maptek allows us to provide a full end-to-end solution, because you can then take their Point Studio software and derive insights from the data that we've enabled the collection of. So today, I'm just going to start off with a bit of an overview of what Hovermap is, and show a couple of use cases in the mining environment, and then I'll hand over to Jordan. So in case you haven't come across Hovermap before, it's basically a system which is designed as a payload for drones and to be mounted on a drone to allow drones to become autonomous. So it's a lidar-based system. You'll see the lidar mounted in the front of the Hovermap payload there, and that lidar actually continuously rotates as the drone's flying to scan in all directions. We use a SLAM-based algorithm to use the system for mapping, so it's providing real-time mapping of the environment. And then, like I said, is also providing autonomy for the drones. So we use the lidar data in real time to provide perception to the drone, allowing it to see what's around it. And we also use that lidar data and the SLAM algorithm to estimate the state, so that's the position and velocity of the drone, without using GPS. And then we build our autonomy control loops on top of that, allowing the drone to self-navigate in these challenging environments. So some basic specs, it's based off the Velodyne VLP16 LiDAR, so we get around 300,000 points per second, up to 100-meter range from the LiDAR itself. We output intensity values, and it does provide dual return. So there are some use cases for that in the mining environment, and so will Jordan. As I mentioned, and you'll see in some of the videos, we do actually rotate the lidar to provide a full spherical field of view, and that's important for mapping in all directions and allowing collision avoidance in all directions. The data, mapping data, is stored on board and then is processed in our software to produce the point clouds. So a couple of images of Hovermap mounted to the drones that we've integrated with. This is a DJI M210, and we've also recently integrated with the DJI M300, slightly bigger platform with longer flight time, but both are well suited for a mining environment, both above ground and underground. And this slide is just to show that sort of the versatility of Hovermap. So I mentioned it's designed as a drone payload, but can also be taken off the drone. We have a quick release mechanism which allows you to detach it from the drone, and then you can actually use it as a handheld scanner or mount it to a vehicle. We have a protective cage which allows you to lower it down vertical shaft. We've also recently started integrating with the Boston's Dynamic Spot Mini, really exciting platform, and looking forward to sort of the integration with that system. And then sort of diagrammatically just shows the various places you could use this in a mine, both above ground and underground. And sort of the common theme is getting into these challenging areas, which are usually very difficult to access, and either use it on the drone or one of the other deployment mechanisms I mentioned. So the way the system's operated when it's on a drone is we stream a live 3D map to a tablet interface, and then the operator simply interacts with that 3D map to set waypoints and command the drone, sending it off into stopes or down drives. And once a waypoint is placed, the system self-navigates. It can go beyond line of sight, beyond communication range to reach those waypoints. It has smart fail-safes, including dust failure. So if it gets into a really dusty area, it will abandon the flight and return home. If the battery's running low, it will do a smart return to home. So it's an incredibly robust system, which allows you to deploy it in sort of these very challenging environments on the ground. One of the most common use cases is mapping of stopes. Benefits here is you don't have to approach the brow, so you can launch the drone from a safe location, send it in beyond line of sight if necessary. And you can see this example, you can see the flight line. So pilots were standing well back, the drone was launched into the stope and out again, all within a couple of minutes, and providing very detailed point clouds from that flight. Let me just drop the audio on this one. So this shows an example of a flight into a stope, very typical stope flight, top entry. Waypoint would have been placed towards the back part of the stope. It's reached that waypoint and now descending to a second waypoint lower down. You can see it's kicking up dust along the way, but the lidar was able to penetrate through that dust and still continue on the autonomous flight and still produce the point cloud. And then if no further waypoints have been placed, it will return to back to the operator. So this flight would have taken around 3 to 5 minutes to map a stope, and obviously compared to the setup time from a CMS, it's significantly less. And as I mentioned, some of the safety benefits as well. Just a few examples of data collected in stopes. This is looking top down, and you can see the level of detail and coverage. So, benefit of flying into the stope is you eliminate shadowing that you would usually see from a CMS. Another scan looking from the bottom of the stope back up to the backs, and you can see the flight trajectory there as well. And just one more example, a section view through a stope, and you can see the flight trajectory heading up right to the top of that stope, flying in between some cable bolts hanging from the backs as well. So beyond stopes, it can be used in many other areas. A few more examples. This is an example where it was lowered down on a cable down an ore pass. Actually, sorry, this was a raise bore. So this was a vent rise for a raise bore, 500 meters lowered down, mapped a significant area of overbreak. Again, all within around 20 minutes of mapping time. And here's an example where the drone was actually flown down an ore pass. If it's not possible to lower it on a cable, but large enough for a drone flight, it makes sense to send it down an ore pass. So this flight was more than 100 meters down an ore pass to map and monitor for overbreak. Can be mounted to a vehicle. So this is a quick example of a suction cup mount to the front of an LV driving down a drive. and then quick fly through the point cloud that was generated from that quick drive down the decline. System can certainly be used above ground as well for doing stockpiles or flying up close to infrastructure to map and inspect. If you've got an inspection camera on the drone, Hovermap keeps the drone safe in those environments, mapping ROM piles and open pits as well. So our workflow is pretty straightforward. I've talked about the flight data, collecting the data. We then transfer it to a laptop or a PC to do our processing, which is drag and drop. And we output a 3D point cloud in standard formats such as LAS, LAZ. And from there, it's ingested into third-party tools such as Point Studio. And that provides the end-to-end solution for our customers.
Say, Stefan, what's the interesting question there relating to the stope and just, the typical size of the stopes that we're doing?
Yeah. Minimum size is often a question. So we can fly through an opening of around 3 meters in the full autonomy mode and around 2.6 meters if it's in pilot assisted mode. And the upper limit size is really no upper limit. I mean, we've never had a stope that's too big to map for the system. Even with the 10 minutes flight time on the smaller drone, we've mapped very large bulk stopes of 100 meters across by and other ones which are within 100 to 120 meters vertical. So in summary from me, I suppose the benefits of using a system like this underground is access to new data, so you can get into areas that you previously couldn't, and that allows you to derive new insights. The efficiency of capturing that data means that you can do this more often. So you can do monitoring of areas and look for changes over time. And also you can do that with less skilled operators. So you don't have to be a drone expert or a surveyor to capture the data. Obviously use those survey or geotech skills in the analyzing the data. And then from a safety aspect, not sending people into those hazard environments is sort of the primary safety benefit, but there's a secondary one as well, is because you've got more data and more insights into the underground environments, allows you to improve safety in those areas as well. So yeah, definitely see this as a key enabler for the digital mine of the future, where you need to constantly monitor and capture 3D data to derive insights. All right, so that's all from me. I'm really excited to hand over to Jordan now, so he can give you a live demo of what you can do with Hovermap data in Point Studio.
Thanks, Stefan. So, as introduced, I've worked for Maptek for a number of years and specialized in point clouds. Now, some people, when they think of Maptek, they're really thinking of one product. Maptek is many products. And in the 90s, we sort of had to evolve what we were doing and start dealing with some high definition point clouds. And you sort of think there, did he say 90s? So we had a contract with Defense and developed software to handle aerial lidar point clouds. That package has then evolved to a commercial offering, and Maptek being very mining orientated, it was obviously a natural fit and finish into that whole mining world. So Maptek dealing with point clouds, we also manufacture laser scanners. And when we saw the Emesent offering, at first it was, oh yeah, another point cloud, yep, cool, we can deal with that. And then we sort of started to see what could be captured with this autonomous level of flight and really that complete data coverage underground, rather than from one or a couple of individual viewpoints, you have a moving viewpoint. And that sort of really took us. Now, on screen at the moment, I've got a stope scan. This is that consume level that Stefan was talking about. This is just a LAS file, drag and dropped in, click and dragged. Once it's imported into our engine, it's essentially a complete copy of that file inside of our database. It's not referenced back to that original file. It's its own little working copy. And it does mean that manipulating and editing this is quite fast. When you do import a Emesent scan, by default, it comes in at an arbitrary coordinate system revolving around the instrumentation. There are ways to coordinate it roughly or match it into other data sets, but we do registration in our software. So to start off with some basic registration, you do need survey control. We can also do cloud-to-cloud registration. We've got automated registration, but right now I've got 4 control points. I can see their mind grid coordinates, and I have a scan. Our software has a nice and easy menu layout, and I'm going to be running through something that's essential for basically target registration using matching point pairs. Now, there's a couple of ways to run this. I can simply click on the target and it will find a local tie point and matched to a fixed tie point. I prefer to create a secondary point set and pick the exact centroid of each target spot. It means it's also like a fixed control point from that scan, or a reference point, tie point extracted from the scan, and not just an arbitrary click. So our view, pretty powerful. I'm just going to quickly create a section to view down one side of this drive. And we can see on screen where our control points are. Next thing I want to do is just change our color scheme. The scanners pick up a reflectivity field, which we call intensity, and it's essentially the signal strength that the laser scanner itself is receiving back, like how bright a return is it receiving. So I'm going to change our color scheme and run by an intensity command, and it will really make these targets pop. So then the next thing I want to do is also filter out my point cloud, and I only want to see these targets. So I'm going to filter by intensity and just remove lower reflectivity returns. Once this is done, we have a nice collection of data that is essentially just those targets. They're going to be in I guess, a matching system. So this is target number 1, that's target number 3. When you're digitizing this, there's no need to have it in any order. There's also your minimum required amount is 3 targets, but you can do 50 and it will do like an RMS fit between them. So I'm going to select the points in this region and create a point in that point selection centroid. And I can see there is a small little X there. I'm going to rinse and repeat. So the next one, point selection centroid. I'll swap my section to that other side. And last point, point selection centroid. So this is, that really basic target registration. I now have a points file that is just those 4 points, and I can run our target matching point pairs. So that are my local tie points. I now have my fixed control, highlight the information you want to register. You have a few options here on if you've got, say, 50 control points, it can remove some from the equation if they're outside of a tolerated error. So you might have one where the control point is incorrect. So click OK. That scan's being shifted. I have a small report on what the original distance between point to control was and the final RMS separation. So I'll close down that graphics view. There's my 4 actual control points from a jigger, and I'll drag and drop that point cloud straight in. So the graphics engine is really, some of that core user interface of software. And I think we take a lot of pride in having a nice, fluid, seamless graphics engine and being able to manipulate point clouds, load on and off other models, and it's all quite seamless. It's not, chugging and churning. Obviously, it depends on the detail of data you're using and the distance between data sets. You notice I didn't load a scan on from a 0 coordinate in the same graphics engine as my tie points because they're a very long way apart. So once that scan's registered, we obviously want to filter out a bit of information. You can see there's a little bit of noise on the outside of this point cloud. So there's a couple filters we want to run. Now, anything you're doing on a regular basis, you can also streamline, one with workflows, but 2 with a bit of customization. So we do have an Emesent toolbar now where we can run range filters and I guess queue up and batch little things. So I have a filtering and modeling section, a registration section, an end of month for underground volumes, and some automated processes. So first off, I'm going to remove information that's further than 10 meters away from the laser sensor at the time of capture. Let that run. So the graphics engine's just updating. And then I also want to remove low reflectivity. And you'll see here quite a drastic change in just point cloud depth or clarity. Like so. Again, just removing those outliers is a big thing. From there, we've got subsampling tools. We have a various set of filters. If you're trying to filter inside and outside of models, above and below models, you can make a pretty big difference in the overall detail of data or continuing an existing job with a new data set. So from there, I would normally create a complex 3D surface, which creates a model of this. Some of our point manipulation and editing tools as well really help with this. And again, I'm going to fall back to that section view mode. And this can help in picking out inner points. We do have methods of fitting loops and deleting detail on the inside of, I guess, underground workings. Just going to put that into a new window. And that section view really, I guess, comes into its own underground. So create a section, 2 points, slice down that drive. And here we can sort of step through and visualize quite quickly what is interior points. And then as far as selecting and deleting, it's simply a quick lasso and delete information you don't want. So cleaning a small area like this, you can do it automatically with loops and trying to extract exterior points. I like to use a best fit algorithm, so the surface traces best fit through points. So the manual process of selecting and deleting will probably take me a couple of minutes. So in this case, I'm going to go, here's one I prepared earlier, and load up a surface. So while I'm still in section view mode, you can see the surface solid that I've generated really does best fit through that point cloud. It's not picking just the interior points. It's not picking just the exterior points. It's that best fit. So once you've done a model, there's various bits of information you can obviously extract from that. Obviously the basics is query solid volumes. We can clip that into existing models as well. So I'll quickly create a copy of that. And you'll see I'm just throwing models around left, right, and center. To join these two together, I'm just going to delete their openings. Grab those. I want to join them. Create a small little tube in the middle. Select all triangles, copy, paste. Now I have one object that is a closed solid and I can get a volume from. So updating existing drives is seconds. And there's my final volume. Now, another example, I've got another stope model from the same area here. There's a couple of things you obviously want to do with stope information. One is conformance against the design, right? I have a design solid here, and this is one that I've gotten creative with. We have coloring tools. A lot of them are used in deformation or change detection. And this is really quick and easy to recognize performance against design. So we can load in existing color schemes. I have a stope reconciliation color scheme, so essentially a distance to design. Oh, I've colored the wrong model. And there we go. It's a quick idea of where you may have blasting problems. So overbreak, underbreak. Again, we've got the same query, differential solid volumes. We can compare solids between each other. So essentially work out overbreak, underbreak as well. So I've got a new solid, an old solid, calculate a mass, and here's a bit of information. If we want to look at that in 3D, we can create a very quick label here. Put that on top of my model. and actually export that out as a deliverable 3D PDF. So it's an emailable PDF document containing 3D information. So some other really cool things here with solids. We have a combination surface tool. Now, a lot of open pit people use this to join pit models together. In the underground space, it works a little bit differently. I want to create a closed solid. I can join these two surfaces together and make the biggest possible solid. To visualize something different, I want to see inside of this stope model, where is my survey drive? Like, where is that double upper volume? So I can create a new surface here. This is the result. And very easily visualize where that drive passes through. There's a couple outlying pieces of triangulation here in that same model. We can automatically clip them out to in a heartbeat. So editing and manipulating models is just fluid. It's the same as selecting and deleting parts of surfaces. We can quite easily make holes. So you can see there I've blown a hole in a surface. I can have a look at that from the interior and also fill them up. If you've got problems with surfaces, we have join and close, we've got fix surfaces, fill holes, and it's quite easy to patch problem areas in triangulations. So from this same stope scan, there's obviously a whole bunch more deliverables we want to extract. One of them is obviously geological mapping. Where there's a change in reflectivity, you'll get a change in brightness. So geology intersections you'll be able to map. There's also RGB coloring available in the Hovermap platform. So we can very easily create line work. One of our cool tools is freehand line. I absolutely love using it with a tablet or a stylus, but with the mouse here, I can just trace down a change in reflectivity, and that line is then projected onto the surface. So you can see that in 3D. All of our CAD objects can be attributed. We can give them feature codes, assign them different layers. I've got coal information here, but you can quite quickly attribute your CAD information. That's really cool. We have a whole dedicated geotechnical ribbon. There's three main methods to extract geotechnical discontinuities. So I guess first and foremost and the most basic is to select a cluster of points and fit a plane to it. So to make that easy and make sure I'm not selecting through both sides of the model, again, I'm going to revert back to that section view mode and just look at one side of the model at a time. Select a cluster of points on a daylighting face. We have some smart select tools to try and expand that. And we have a query discontinuity tool. That's going to give us a quick dip, strike, dip direction. That information also has length and area associated with it. You can attribute it and give it a joint set and roughness and other geotechnical attributes, change the symbol. And that's a very manual process of going ahead and digitizing discontinuities. We've also got two other tools which are far more automated. And to make it easier to see these discontinuities, we can make them pop, just like intensity, but using color by direction, color by dip and strike. And you'll see here when I rotate, daylighting faces that have a very similar direction are colored that same color. I'll just turn off section and pan around. And you'll see that quite clearly. So going through and extracting them, we've got two tools. We have a smart query tool. And this is probably the most recommended one for a thorough result. It allows you complete control in where you map. And that is by manually clicking. We can extend those planes, but I'm in control on exactly where these faces are being produced. So that's a semi-automated process. If I just turn off my model, you can see these little planes appearing. So we can go through that and click out a lot of planes. The completely automated tool is also still quite valuable, but you do need to tailor the thresholds to ensure you're getting valuable information. I'll just pop my section on again, so I'm only selecting one side. And here you select one face, and it will identify all faces within this threshold. So it's detected 168 planes that match that original selection. So I'll save them out. I'm going to do this a couple of times here on opposing faces, and we're going to throw them in a stereo net. So again, that complete coverage of a stope really gets you, I guess, a visibility of daylighting faces that you haven't seen before.
So, Jordan, just a geological question, and I may have very poorly timed this question that's come through. Just a question from Saut. Apologies if I got the pronunciation wrong, but can we generate a solid based on the color image rather than using polyline to generate the boundary?
So you want a solid surface of the certain geological section. To do that, you would essentially create a polygon around that intersection and crop out that small area, and it will retain obviously its shape and its exact boundary. So that, I guess that's a solid of that 2D slither with minor 3D information. It's not a full section. If you've got multiple drives, you can build things together to try and digitize where you may have I guess a matching geological trace. So
nice. Feel free to put some more detail in that question box, and just a reminder to everybody else to please jump in and ask those questions. Jeremy's been kind enough to answer a few of them as we go, but always more welcome, and hopefully still have some time at the end. So sorry, Jordan, back to the show.
Cool. So I've gone ahead and created a few different selections here. Once I have these, they're essentially called sets. And you'll see as I rotate around various little sections, there's still a few that haven't been picked up. So I'm just going to quickly add a couple more. Spin that around. I want extract again. Punch that out. There we go. All right, so these are all discontinuity sets. There's lots of editing we can do to these discontinuities, but just to visualize things, we can throw them on a stereo net. You can add in planes and intersection points on that same stereo net, but it does allow that quick visualization. So nothing to really highlight where you may have overlapping sets. I prefer contours because it really does highlight where things merge together. So there's obviously a set here at a very similar orientation because the contour has wrapped around it. That crosses over. So another cool thing about Studio is there's no real limit to the number of graphics engines you can have open at any one time. We can lock views together. So at the moment, I've got my Geotechnical view. If I want to add in just the survey solid, I can add that on top. I can also add that to a whole nother graphics engine and lock those two together. So there's an option here, tile and tie. And here I've got two independent graphics views. So one's sectioned, one's not. And visualize things in a different manner. And I can load the original scan file on there and have a look at that too. So moving on, one of the things that I specialize in as well is automation. Now, automation in Point Studio, we can deal with Python scripts. We have a complete Python SDK. We've also got a tool called workflows. Now, our workflows aren't me prompting the user, hey, do this. This is the next step. It is a complete automation. So as an example, I've got change detection. Now, change detection can be deformation. It can be just looking for, change in material. Has somebody excavated there that we didn't really know of? Are you trying to do stock loss and tracking? It can go one step further and do complete, automated deformation, automated shotcrete reporting. It's that change between two objects. So this is a workflow and it is automated. So what is my new data set? Well, in this situation, it's scan number 2. My original data set is scan number 1. I'm going to be using surfaces to color against because it's that best fit rather than using just a point cloud. predefined color schemes. If you're doing geotechnical deformation monitoring, you might have a completely different color scheme depending on the area, and it may match a TARP level. This example is shotcrete, so I have a one-way shotcrete color scheme. So I'll load that in and click OK. This is going to automatically register them. At the moment, my point clouds are thousands and thousands of meters away from each other, so I can't load in scan2 just yet because it's at that 0, 0 coordinate, but I'll click OK and off we go. So the only information you can see is this little preparing. This will take about 2 minutes to completely run through. So it's registering, it's doing multiple iterations. I can load that scan on screen now because it's done that original batch bulk transformation. And we'll see these 2 point clouds slowly line up. So you can see there's still a little bit of difference. It's going to do multiple iterations. It's going to create a surface with best fit and also squeeze that surface together to really get a nice intersection. And deformation really does rely on accurate registration. Target registration alone, I don't find gives you that complete, locked in, I guess, accurate model. By allowing the computer to run a predefined, known set of steps with multiple iterations, we essentially eliminate all, my user experience as an experienced user, I guess, controlling the software. It allows standardization across your teams to produce consistent results. And that's my big push for automation. While we wait there, we've also got other reporting tools. So we've got obviously volume reporting. That's great for stockpiles and whatnot. We do have an underground reporting tool. And this is great for looking at drives to drives, right? Drives to design. It gives you overbreak, underbreak analysis for left, right, front, back with heat maps. It also generates contours or sections. So, and it is a nice report showing my drive design and my drive as built, the RL and the section width. So that is quite a nice report that you can send on to other crews, other team members that aren't used to seeing 3D detail. It's a nice 2D automated report that's generated. So this workflow is just about done. Bingo. The result here, there's my colored surface, and quite easily see change. If I load in my original surface, the registration between these two you can see is near perfect. I've got a nice intermottled surface. I'll just change the color of that base to make it highlight more. And again, that section view really comes in handy to identify areas that have changed. In this case, shotcrete's pretty obvious, but my 2 surfaces here are perfect. I'll scroll through and you can see that thickness has changed where they have applied that shotcrete. So automation is fantastic. Another thing I love our automation for is stockpiles. So stockpile reporting in volumes, we can always do with polygons, of course, and pump it out to a CSV. I like to go a little bit next level and use workflows to create little 3D labels and a 3D PDF. And it's a nice 3D object that end consumer can visualize. So I've got some boundaries here. I need to quickly update this stockpile boundary because the stockpile's changed since last month. That boundary is called yellow-green. So what I need to do is update that line. So I'm going to just quickly draw that new polygon. And again, I love that freehand line. It's just click, draw, and away we go. If that's hard to see, I'll just increase my line thickness. There you go. Now I need to update that polygon with that new line. So I'm going to break this existing polygon. Select that old chunk, delete it. I now have these 2 lines. I've run join and close. I have a new polygon and we're ready to rock and roll. So I can query volumes right now, but for something different, we're going to run through an automated workflow that's going to triangulate multiple times. So data set to triangulate, what is your polygons? what's your surface prefix? So 210324 for the date, and hit go. So this is going to create multiple triangulations of this area. And we'll see them pop up on screen. There's my little finds. Now I do get a little bit carried away when I'm working with this software. I'm quite passionate about it, so I hope you're hanging there with me. And this workflow is essentially looping over a process, triangulating the same data set over and over again. So rather than using a different tool to split by polyline, I'm retaining the name. And the reason I'm doing that is to save me manually renaming things. It's that less user input, less chance of an incorrect key strike, and can make reporting easier. So I'll decrease my lines. Just about done there. So this stockpile data set's really nice. Again, the same thing here. I do recommend using tools to best fit your point cloud. If I go into my default mentality of an open pit area and pick the lowest points, you're not getting the true representation of this data type. If I quickly visualize this, you will see what I mean. Looking at a point cloud, seeing my surface and being smack bang in the middle of that point cloud. It is a mean, it is a best fit, and it is the best way to get information out of this data set. So my topographic triangulations are done. Next thing is, well, how do I report this? Well, we've got query surface volume. We've also got a nice fancy workflow that automatically creates labels. So what are your stockpiles? What's your base? Hit OK. This is going to run through and create a small 3D sign with the product name, the date, and the volume. So this same thing you can use in screenshots, but also that 3D PDF, that depth. So our 3D PDF tool is this button here. So that is done. Let's bring back our base. Change the colors of all our surfaces. We've got lots of different color tools. I'm going to add a little bit of height here. So I want to color by the Z coordinate. I want to blend with an existing color. And here you can see just that little bit of depth and detail assigned to my stockpiles. So that was a bit of Emesent data in Maptek Point Studio. Point Studio really is that sort of do-it-all point cloud editing toolset for that mining environment. Working with Emesent, we do have this Emesent menu with a bit of customization, and it does allow, I guess, new users to jump in and be quite quick. If ever you get stuck and can't find a command, we do have this great search tool. So I want to reduce detail, I want to simplify, and I want to simplify by distance error. You get a small video that pops up, and you can remove detail from a triangulation that has no accuracy impact within your threshold. So
that is absolutely incredible, Jordan. I think I'm going to have to watch the replay of this video 2 or 3 times. Each time I see Maptek being demoed, there's more stuff and more things under the cover there. So hopefully even some experienced Maptek users discovered some little Point Studio secrets there, and yeah, get a masterclass there from the master at work. Absolutely incredible.
Yes.
And I must say, rather cool to see an Emesent button on the screen there. So the toughest of questions, got just the guy online to answer it. The classic accuracy question has come through, which is great. We get that all the time, and I'm going to throw over to Dr. Jeremy, and just as I find the exact wording, but it's the usual sort of what's the accuracy, and to match in with today's topic, what is the accuracy and the smallest deformation that the device can capture?
That's a great question, and it's definitely one that we're asked quite often. The short answer is that generally we start to think of Hovermap data in centimeter scale. So 1 to 3 centimeters is kind of our generic answer. And the reason we have a generic answer is because the real answer is far more complex Accuracy is very much dependent on the range of the hover map to the target area. So there's range noise that affects accuracy. So the closer you are to a target area, the more accurate those points are going to be on that surface. The environment itself can play a factor, but underground, the range is usually pretty low, and the rock material provides a great surface for reflecting off of. So again, 1 to 2 centimeters in the underground environment would be a typical or expected outcome. As far as the resolution, so how fine of a detail can we see in an image? Again, that's another factor of range. The closer we are, the more concentrated the points get, and we can start to pick up on smaller features. We are able to see fractures in rock and other joints within the geotechnical surfaces, and we're able to pick up on small changes that, like Jordan had covered, in shotcrete. So, you know, small features, it's hard to quantify that particularly, but again, think centimeter scale, and I think that that would help manage expectations.
Nice. Another hot topic that we're hearing a lot about, touching on convergence monitoring. Question here from Savannah around that compliance report you brought up there before. Would that potentially be an alternative way to demonstrate and report on convergence?
I think part of the tool does require sort of closed solids to be created. So in the fastest workflow possible, we're doing a modeling technique that doesn't retain that full perfect solid. Normally we subsample a bit to get a nice survey style of solid for volumes. That being said, the automated cross-section side of it is a great way to represent things. So there's probably a workaround there as a alternate way of presenting things. The downside is, sections don't cover all the detail. So it's really, you're referring back to that heat map to get that full visibility on where things have changed.
That was the second part of the question.
Yeah,
that, do you still need to go back to a heat map, which seems to be the common.
The other way to do it is we can manually create sections. There's a create parallel sections tools and an arbitrary section tool that creates saved out CAD lines in whichever direction you want. And those you can either export out to other software packages or print, plot, do differently. So.
Nice. And I will say that we had planned to finish up at 45-minute mark. We're a little bit past that now. I'm happy to keep taking a couple more questions. There's some great ones there if you folks are too. There, just to say again, there will be a recording available. So let's just maybe do a couple more questions and wrap it up. But of course, we've got copies of these questions so we can get back to folks and answer any of those things we don't manage to cover. Is the Emesent tab paid add-on or a new update to Point Studio?
I think keep your ear to the ground, Savannah. We can probably help you out, but we're working closely with Emesent to fine tune these things and make sure we're allowing the customization that people need, and I guess firming up tools. Those existing iSight or Point Studio customers, the range filter in our standard filters is designed to filter a stationary scan. So the range filter that I used is a bit of a hack job we slipped in with Python. And that is the beauty of our Python SDK. We can very quickly work around these issues and add in functionality.
Lovely. Okay, one, Stefan, you're not getting off the hook. A question around, we always get asked about IP ratings and like, but what is Hovermap like around sort of a wet environment?
Great question. I mean, obviously it's used underground around the world in obviously harsh environments. IP rating is around 43. It hasn't been officially tested for IP rating. Obviously, that's when it's drone mounted, the drone has to survive those conditions as well. Hovermap is usually mounted underneath the belly of the drone, so it does provide protection from above. And we've got some videos online of drones flying through, water dripping from the backs, kicking up a lot of dust, and it survived those sort of conditions.
It definitely takes a licking. It has been tried and tested in some of the craziest environments. Just doing another quick scan. I do apologize if I, that's trick questions.
And hold back. I'm ready.
Okay. Be careful. Why? I think it was, why is Maptek better than Cloud Compare?
So I like Cloud Compare. I'm all for open source too. Cloud Compare is great value for money, right? It doesn't have standardization, doesn't have automation, doesn't have databasing. You can't really do the exact same thing twice and get the same result easily, unless you have a lot of training. We try and alleviate that. We've got a lot of experience. Our graphics engine can handle millions and millions of points without this weird jittering, you know. But ultimately, Cloud Compare is great value. So
I would just add that Maptek's capabilities for reporting are exceptional as far as the workflow on the mine, and there are no reporting mechanisms that I'm aware of out of Cloud Compare. So being able to visualize data and work with it is an important aspect of everything, but being able to convert that into actionable reporting is critical. And I think that the Point Studio and the Maptek software suite nail that 100%.
Awesome. Yeah, huge thanks to Stefan for giving us the overview there. Jeremy coming in and answering a bunch of the questions, both live and in the Q&A panel. That was fantastic. And of course, Jordan, it was just great to see you driving that. Like I said, I'm going to have to rewatch that a few times to really wrap my head around everything you can.
Obviously, any questions that haven't been answered, feel free to reach out direct. If you're in different regions, feel free to contact other Maptek offices as well. We're all on that same sort of page. So.
Lovely. And a huge thanks, of course, to the broader Maptek team for hosting us today. It's been great to try this on Zoom rather than our usual panel. It's been, nice change of scenery. Great to be back doing the webinars. And we're going to throw up a poll just at the end here. If you're still online, please take a moment to just let us know how we're doing. Thank you again, team. It's been great to have you along today. We will catch you on the next one.
Great, thanks Pete, and thanks Jordan. Definitely wowed me again. So congrats, and thanks to everybody on the Maptek team.
Thank you.